So we've looked at training. Training is actually relatively easy, right? So you feed in the output the next from the previous prediction to the next time step, and you train. We've looked at test time, what you can do. You can do greedy search, or you can do something slightly better like beam search. And then we haven't looked at evaluation of blue, but I'll explain that in the next lecture. Okay. So is there anything left? And you guys have actually picked up on a number of issues with this model already. Okay. With this approach. So beam search solves or tries to solve one of the problems. But can you think, I mean, you guys have thought about a number of issues already, so let's just spoil it for you. The one crucial problem with this model, with just encoder-decoder, is the following. If you have the input sentence, you're compressing that whole sentence into a single vector, okay? And then your decoder is asked through this like recurrence here to actually even remember this compressed version of the input sentence. You can deal with that by feeding it in every time step, but you still have this problem that I've summarized this whole thing into a single vector. Okay. In practice, what often happens is this is a 4-word sentence, really short, but if you're translating any realistic sentence, I mean, just this short sentence here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 words. Okay. These sentences can get quite long. Okay. And then in practice, what often happens is this final representation here is influenced most about by the words at the end of the sentence. Okay. So the stuff here at the end influences this, and then you're asking the decoder, listen, output the first word, which probably has something to do with stuff starting at this start of the sentence, but looking at this one vector that's supposed to summarize everything in life. Okay. Does that seem like a problem? Yes? Yes. Okay. It turns out to be a major problem. It's related to what Leanne asked. If one of the words here switches from me to it, then you're asking this vector to change in a way so that you can actually encode that during decoding. Okay. So this is where attention comes in. Attention is like there aren't that many things in machine translation that in NLP that really shook the whole research community as much as attention. Okay. Actually, if you think about machine learning, neural networks were figured out in the 80s, right? 80s, 90s. Okay. And then in this revival, there's a few tricks, a few core things that really changed the neural network landscape. Using ReLUs instead of sigmoids, that changed things. Getting GPUs, that changed things. But there's a handful of tricks really that changed from the 80s and 90s. Attention is one of these things that really changed stuff. Okay, so it's really worth thinking. And I'll just explain it on this diagram here just very briefly. The idea behind attention is the following. When I'm trying to predict this word through here, okay, actually I've seen here and I fed that in and I'm figuring out what should I predict next. Standard encoder-decoder can look at two things. It can look at my hidden state that's saved from a previous time step, and it can look at my current input. That's the only two things it can look at. Okay, that's it. Attention changes this. So what attention will do is it will say, listen, I'm trying to output this word here through, trying to figure out what to output. Okay? Instead of just looking at the previous hidden representation and at my current input, what if I could look back to everything in my encoder, all the different time steps in my encoder. I'm going to look back at all the different time steps in my encoder before I output this word. And that's how attention works at a very high level. I'll go in a little bit more detail even. What it does explicitly is it says, take the hidden representations, all of them in my encoder, and take a weighted sum of those representations. You're literally going to get a new vector from these representations, a new vector, which is a weighted sum of these hidden representations in my encoder. And then before I output, make my final output here, I'm going to look at this weighted sum, which is just a weighted version of these vectors. Okay, and I'm going to basically get that vector in here, concatenate it to my other hidden representations, and before I predict the word through, or before I predict the word at the second time step, I'm allowed to look at this vector. Okay, that's the basic idea behind attention. Now, just as a reminder, it will seem slightly complicated now. If you can do a forward pass through your neural network, then you're done, right? Then PyTorch takes care of the rest, as long as you have the gradients with respect to the little blocks. So even though it isn't actually that complicated, even though it might look a little bit crazy in a second, if I can do a forward pass, I'm done. Okay, so just keep that in your head. Okay, let me expand even a little bit more. What we will do is we will take this vector, the hidden thing in the decoder, and then based on this vector and each of the hidden representations, I'm going to take this thing and I'm going to, according to the two of them, calculate a weight alpha 1 for the first time step. Then according to this vector and this vector, I'm going to calculate a alpha 2. Okay. According to this vector and this vector, I'm going to calculate an alpha 3. Okay, and so on. And then this vector here is just going to be the sum of this vector times the scalar alpha 1 plus this vector times alpha 2 plus this vector times alpha 3. That was very high level. Now I'm going to go into the detail, and then I think it will make sense. It's called attention. It's called attention because based on this vector, I can look back and I can attend to different parts of my input sentence with different weights, with these different alphas. Okay, are you guys with me? Okay, cool. Let's go not through that math. That looks a little bit too crazy. Let's just go from here. Okay, I'll do the forward pass for you, and if you have the forward pass, then you're done, right? Probably use my notes. Okay. This is how the forward pass works in my decoder. Okay, I have my current decoder output. My current decoder hidden representation. I've already passed everything through my encoder, so I'm done with that. Okay. Then what I do is I take this green vector and I take this blue vector and I calculate, for now, the dot product between the two. So I literally take the dot product between first blue vector and this green vector here. Okay? The dot product between those two things, two vectors, I take the dot product. What do I get out? A scalar, and with a real number, so it can have values of minus infinity to infinity. Okay, cool. So that number there, that's the dot product between this thing and this thing. Okay, I'll just draw a little arrow here. Yeah. Okay, cool. So that you know that that's the dot product. I take the dot product between the next time step and this green vector. Now, okay. And I continue with that. So I get a bunch of scalars here. Now, okay, I get all these scalars. I'm not drawing all the arrows. You with me? Okay. If the green vector and the blue vector is more similar, the scalar will have a higher value. Okay. Cool. These values are between minus infinity and infinity, but what I want is I want to squash them to be between 0 and 1. Okay, and I want one number to be higher than some of the other numbers. So what I do is I take these values and I push them through a softmax. Okay, I'll draw it like this. Okay, so we push them through a softmax. Cool. What comes out of the softmax? Stuff that looks like probabilities, that's right. So a bunch of numbers, and those bunch of numbers sum to 1, and they're all between 0 and 1. Okay, and I call this number alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5 in this case. Okay, cool. Now what I do is, okay, the idea is basically that based on this vector, I can look at my input and I can weigh them according to how much I care about my inputs. Okay. If alpha is high, it means that based on this green thing, I'm really looking back at that specific time point. So you might have, I'll draw this out and then wipe it out, but if we're at the start of the sentence, we're probably looking at the start of the previous sentence. So this alpha might be really high, some very high number. This is a bar graph here. Okay. The second alpha might also be pretty high, but then these alphas might be pretty low. Okay. Okay. And those numbers, they sum to 1, they're between 0 and 1. Okay. So that's the basic idea. I'll repeat that in a second. Okay, cool. Now we've got our alphas. We're obviously not done with our forward pass because, we haven't actually done any decoding. Okay, so what we do now is I take this vector, the first hidden representation. I take that one and I multiply it by alpha. Okay, alpha is a scalar. Okay, so this is just a scaled version of this one. I take this thing and I multiply it with alpha as well. Okay, you with me? Cool. And I do that for each one of these. Points, I multiply them with their corresponding alpha. So the fifth time step gets multiplied by the fifth alpha. Okay, I'm just scaling the vectors. Okay. Multiply, multiply, multiply. And then what I do is I add them all up. And then I get one context vector. It's almost like my red vector from before. And we normally call it C. Let's draw it in red as well. And this vector here is now a summary, it's a weighted average of this, and it's a summary of all my input hidden representations given that I'm at the current time step. Okay, with me? Okay, we still haven't got any output yet, so that's sad. Okay, so now what we do is we take our current hidden representation here and we concatenate them. So take a cat block. I take this thing and I concatenate it here. So if this thing was 100-dimensional and this thing is 100-dimensional, then what pops out here is a 100-dimensional vector. Okay, and that vector I then use to predict the output at time step 1. In other words, to figure out what needs to happen at time step 1, I can look at the current decoder hidden state, but I can also look back at all my input states, and then I can decide what to output. Does that make sense? Cool. What do we do next? We have our next state. During training, we will obviously feed this with the ground truth word, so the word he, okay? And then what we do is we take this green vector here, and we get the dot product between this thing and each of the blue vectors. We get alphas, we get a new red vector. It will be different from the first time step. So this is C1. We will get a new red vector, which is different from the first time step. We will get a C2. We will feed C2 back here, and we will get Y hat 2 at the second time step. So the network can decide, listen, I'm now at the second word. I've already looked at stuff before. What should I look at now in my input in order to predict Y hat 2? Okay. There's again a concatenation, but here you concatenate C2. Okay. Third time step, again, you look back, you look at everything, you calculate a weighted average, you use that context vector, and you feed on. Okay. This is what you asked me yesterday, that you have this problem that the last stuff in your encoder normally matches most when you're going on with life. And in the RNN in general, the last things, even in the LSTM, the last things in practice normally matter most. But now with attention, you have the ability to say, listen, this thing right at the start should matter more than anything else. If I've got an attention weight of 1 here and zeros everywhere else, then my context embedding literally turns into my first hidden representation in my encoder. And I can use that in order to output my current time step. Okay. Does that make sense? Yes? Christian? Ish? Yes. Okay, cool. Let's just step through that again, but just with more fancy graphs. So this is what happens. Sorry, this little dot here means concatenate now, that little dot there. So just to recap everything, you take your hidden vector here, you dot product it with this one, you get that value, that one, you get the value here. These values are between infinity and minus infinity and infinity. Very often we denote these as A. So it's like A1, A2, A3, and then you transform that into your alphas by taking the softmax. So the softmax, it does two things, turns it into probabilities, but it also means there's a softmax in there. So that's what the name says. So it's trying to push one of the values higher than the others. Okay. So you get out these alphas, they sum to 1, they're between 0 and 1. You take the weighted average of this thing with the alpha, that goes in there. This thing with its alpha, that goes in there, and so on. Then you get your context embedding here, your C1, okay? And that's then what you feed in before you predict the output at that time step. Yes? Makes sense-ish? Okay, let me run through it and then I'll say questions. At the next time step, exactly the same thing, but now your alphas here at the top changes. Right, because I'm taking the dot product now with this thing, different alphas, and I go to the next time step. Now, I deliberately drew these alphas in a way so that it makes sense. So when I'm trying to predict the first word in my sentence, I'm probably looking at the early part of my sentence. So I've got high values here. Okay. As I'm moving through, now the interesting thing about this sentence here is that in the Afrikaans sentence, the word for through, gegooi, is right at the stop, right at the end. Even though in the English translation, it's early on in the sentence. And the cool thing about attention is this allows you to actually, instead of just going dunk, 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 you can actually jump around and say, oh, I'm at the start of the sentence, I'm looking here. Now, I know in Afrikaans actually verbs come at the end of the sentence very often. So then I'll jump to the end, look here, okay, and then I can jump around and attend to different parts of my input, okay. So, and then for the word me, just looking at the center, and so on. And then right at the final time step, you would do exactly the same thing, and you would, sorry, that should be a green vector, but you would get your new green vector here, you would get its attention weights, and you would get the final output here, and you would try, your target variable would be the end of the sentence. Okay. One more thing to note is you can still do what we did with the encoder-decoder model, and you can actually still initialize the first decoder state with the last encoder hidden representation. That's fine, you can do that. So then the model can actually use this as a summary vector for all of this, but the model can also then look back at all of this stuff. Normally you don't need this. So the famous paper, this is not where attention got introduced, but for transformers is called attention is all you need, because they actually show you don't need recurrence even. Okay, but this is the encoder-decoder attention. Does that make sense? Okay, cool. I'll take questions later.
The architecture completely makes sense, but what's the kind of guarantee that this dot product that you're taking has any meaning? Like in terms of like the start of sentence character, and then you're taking the dot product between these kind of arbitrary stuffs, and then you believe that somehow it's going to, these two dot products mean something in this latent space?
Yes. You have no guarantee. You have absolutely no guarantee.
But it works.
No. No, sorry, it does. No, it does work. What you're doing is you're giving the model capacity to do something. Okay. Let me just restate that. Obviously this is based on some intuition, but strictly this model is more powerful than the encoder-decoder model, right? It has the capacity to look back over the entire encoder space, which the vanilla encoder-decoder model doesn't have. Okay, so this model has the ability to look back over all the stuff that happened before, over this stuff, and use that in order to get my current output. Do you agree with just that statement?
Yeah. No.
It's not saying anything about meaning. It's just saying this model has the capacity to look back and actually
analyze something. But
analyze something. Okay, yes, stop there.
Okay.
That is, in my description, I have this like, hy het my gegooi, he threw me, and I'm looking back at parts of the sentence. The model doesn't need to do any of that. Okay? The model can. The model has the capacity to do what I explained, but it doesn't have to. If it learns something else that's more useful for it in order to do the task that you're training it to do, I'm very happy if it does that. Okay? If it does something completely different from what I intuitively explained, I'm fine with that, as long as it correctly translates from the input to the output. Okay? So we're giving the model capacity to do something which matches our intuition, and I should say machine translation people have actually analyzed these models and see that they do this thing, where they look at a different part of the attention, and you can visualize it. You can actually visualize attention and see that empirically it matches this description. But it's important, you're not giving this model any ability to reason, okay? And you're just giving it the capacity to look back over its own encodings. And that's it. Okay, cool. This is vanilla attention. This is the basic version of attention in an encoder-decoder model, and there are variants of this approach. So I'll quickly just talk through some of the variants, but I'll also talk about it a little bit more generally.